All right, so fluids, electrolytes, and acid-base balance. If you guys love chemistry, you are going to love this whole section. If not, you're going to be in agony. Okay. But I'm going to teach it as though you already know some of the basics, but we'll go a little bit deeper into it in a moment. And you'll understand this little quote I kind of got here. You're a 10 on the pH scale maybe because you're basic. It'll make sense to you when you're on the pH scale. Okay, so let's go into this. And you're going to see, especially when we do the acid-base stuff, that's going to deal with respiratory and urology together. So, and a wonderful reaction is going to pop all over the place in this PowerPoint. All right, so fluids and electrolyte balance. Okay? So we have this homeostasis that we have to have. Now, when we have zero balance is basically the amount of fluids coming in has to equal the amount that's going out. And that's what we really want in our system. We can have a situation where our bodies have to try to adapt, or there's a disease process where we might have positive or negative balance. And positive balance is that we have more in than we have output. So think of things like we have kidney disease. You're drinking a lot, but you're not peeing out a lot. Does that make sense? All right. Or we have negative balance where the output is going to be a lot more than the input. You're eating normally, but you might have diarrhea, and you're pouring out water that way. Does that make sense? More than what you expect. You get dehydrated. But we should always try to have the input equaling the output. When you become nurses, if you're going to go into that field, you'll be doing this quite often with all your patients because we have to keep track of this. The amount of fluids coming in, whether it's through the IV or the fluids that are taken by the mouth, should equal the amount of output, and they'll be collecting the urine or collecting if they just had surgery, how much blood is coming out of their wound, and you'll be collecting that too. Okay? As plasma concentration decreases, the urine must increase. Now just think about that. As the plasma concentration decreases, that means if it gets more dilute your blood, then we have to get rid of a lot of that water so that the concentration goes back up. Does that make sense? Think about that. If you have, I'll use this quite often, if you have your lemonade and you have water and crystals in there, but you have, let's say that, just for our purposes here, 1 cup of crystals equals 1 cup of water, and that's perfect. It's not, but let's just use that as an example, okay? If we put 2 cups of water in there and 1 cup of crystals, it's dilute. That means the plasma concentration, the concentration of lemonade is decreased, it's dilute. So in order for us to get it back to the concentration that we want, we have to lose water. So we have to take out the water, leave the crystals there. So if the plasma concentration decreases, the urine output must increase. Does that make sense? If you think about that scenario. Okay? So the input, we'll deal with that first. Our input over here is mainly liquids that you're drinking. That's easily calculated. Food, it also has some water in it. And metabolic water. Meaning like all the metabolism that goes throughout your whole body, all the metabolic reactions give off water too as a byproduct. So we have to also calculate that that's added water to your body. So that's where our input is. Pretty much we can calculate the liquids and food to a point. It's difficult to calculate metabolic, but that's a smaller amount. The output over here, the biggest amount is going to be urine, of course. And we can calculate that, how many milliliters of water come out of there. But then there's this insensitive water loss. Things that, during sweat, you can't really calculate that. Or when you breathe, water droplets come out of there too. That's an insensible loss. We can't really calculate that with the sweat, the exhaled air, and feces. But the majority we can collect is this. And the majority we can collect is this. Okay? Now, how is the water distributed through our body? Well, 60% of our body weight is water. Okay? 60 to 70% or so. But we'll say use 60 as a number here. So if an average man weighs 70 kilograms, which is about 150 pounds, we could say that that person's total body water is 70 times 0.6, which means that there's 42 kilograms of water that's in your body, or we could say 42 liters. We could do that conversion. So it's 42 liters of water. Now we got to figure out the water that's in your body, where is it distributed? Is it inside the cells? Is it outside the cells? Is it in the blood? Well, that's what we got to do. Okay? So we have extracellular fluid, right? You've been talking about that, the ECF. And that makes up about 20% of the total water that's in your body. Only 20%. Okay? Now this includes the plasma, so we're talking about the water that's in your blood, the bloodstream itself, and also the interstitial fluid, which is the majority of the fluid in the extracellular fluid. The interstitial fluid is basically tissues in between the cells themselves. So that accounts for the extracellular fluid. But a majority of the water that's in your body, which is the other 40% of the total body of water, is going to be inside the cells. The cytoplasm is what you're looking at. Okay? So we can actually put I know you guys love formulas, but you can calculate that if we know certain numbers. In other words, if we know that the interstitial fluid equals the extracellular fluid minus the plasma, that's easy, right? Just calculating that. The intracellular fluid is the total body water minus the extracellular fluid. All right? Pretty easy to do that if the numbers are given to you. Okay? Here's just a picture form of what we just explained to you. Right? So you have the total amount of body fluid in here, water. All right? So you got 60% of your body weight is this. 40% of that is going to be in your cells themselves, intracellular fluid. And you're going to have 20% of it out in your extracellular fluid. That can be broken down into two things. Interstitial fluid, the fluid in between the cells, and in the plasma, in the bloodstream. Not inside the red blood cells. I'm talking about just the bloodstream itself. Okay? Is that clear? That should be just easy subtraction kind of thing. All right. So what's in this body fluids? Okay. Water is our universal solvent, meaning that's what we're going to use to dissolve things in. All right. If you have crystals and you got water, the water is the solvent. The crystals are the solutes that are going to be dissolved in the solvent to create the solution. Does that make sense? So we got solvents, we got solutes, and we got solutions. So the solutes are the actual crystals of the lemonade. What that's made up of is basically electrolytes and non-electrolytes. Things that have charges, electrolytes, ions, and non-electrolytes, things like glucose, lipids, creatinine, urea. Okay? Electrolytes seem to have a greater osmotic power than non-electrolytes. Meaning, as we talked about osmotic power, the Starling's forces, we also refer to it as oncotic pressure. Okay? What it is that if there's more ions there, or electrolytes, that tends to draw more water towards it than glucose, the non-electrolytes. Now don't get me wrong, glucose is going to draw water, but it's not as magnetic, if you want to use that, as the electrolytes with charges. All right? Now, you should know this. We've dealt with this before. The most common cation that's found inside the cell is going to be potassium. Right? You learned that from A&P1 and probably from other classes, chemistry and stuff. You need to know that. All right? Cation, again, is a positive charge ion. Okay? So the most abundant cation inside the cell is potassium. We learned about this when we dealt with the action potential of the heart, right? The most common, or the major anion inside the cell is going to be a phosphate ion, which is PO4 with a negative charge. An anion is a negative charge electrolyte. Extracellular fluid. What's the most common extracellular fluid? Or I'm sorry, what's the most common cation outside the cell? Sodium. Okay? And what's the most common anion outside the cell? Chloride. Right? So that's where I kind of showed you once before our little our salty banana. Whereas the banana represents the cell. And inside a banana, it's loaded with what? What did you learn in kindergarten? It's loaded with what? Potassium. All right? So we have a major cation. All right? And just think of, when I think of cation, just think of a cation has a positive charge there. All right? And the anion is a negative charge. Or think of a happy cat, whatever works for you. Anyway, so the most abundant cation inside the cell is going to be potassium. The most abundant cation outside the cell, what is salt referred to as that we've learned since kindergarten? Sodium chloride. So that means we're going to have tons of sodium chloride outside the cell, as much as we have the chloride here also. But inside the cell, it's going to be loaded with potassium and also phosphate. Okay? Those you need to know. Okay? So plasma, when we deal with the extracellular fluid, plasma and interstitial fluid are similar, except plasma tends to have a little bit more proteins in there too, as we learned with oncotic pressure, dealing with that when we dealt with edema. But what we have here is that the most common cation outside the cell, in the extracellular fluid, is going to be sodium, and the most common anion outside the cell is going to be sodium. You need to know those, okay? This is, for your own sake, if you want to see how much these sodium, potassium, calcium, how much these are on outside the cell versus inside the cell, is a little chart here we could see what that is. Okay, I wouldn't test you on that per se, except for these four over here you should know. Okay, the sodium, chloride, phosphate, and potassium. Now, plasma is 70% or 7% of it is proteins. We've learned that. Now I'm giving you a number. We know that proteins are in the plasma, but 7% makes it up. That means that 93% of it is water and everything else, all the other electrolytes. Does that make sense? Just simple math on it. 7% is proteins, 93% is everything else. Okay? So we could say that there's slightly more ions in plasma water than the total amount of plasma. This is plasma water, where it's just water and everything else. So therefore, that's more concentrated, with, well, at least have more ions in it, than if we start throwing in the proteins too, because now the proteins make up 7%. Does that make sense? Right? That we have more ions in plasma water than in plasma altogether. All right? Plasma has the proteins there, but we say plasma water, then it's everything but proteins. So let's talk about hyperlipidemia. This is a condition where there's an increase of lipids in the bloodstream. It leads to atherosclerosis, that kind of stuff, right? Cholesterol. So what's happening here is, let's say someone's got hyperlipidemia. And in this person's case, 30% of the plasma is lipids. A lot of lipids in there. A third of their plasma is lipids. If we have still 7% of the plasma is proteins, as I just mentioned to you before up here, then this water decreases from 93% to 63%. Which means that the plasma concentration is really concentrated. You see what I'm saying? It's effective because the lipids are counteracting that. It's like pushing that off to the side, so it's making the water go from 93% to 63%. And that's going to seriously affect things with a person's blood. Okay? Now, concentrations of solutions, all right? The intracellular fluid concentration should equal the extracellular fluid concentration. When we put things in brackets like this, we're talking about the concentration. And that's kind of a universal thing that you'll see with chemistry and physics and stuff. So the concentration of intracellular fluid should equal the concentration of extracellular fluid. They have to be equal. Otherwise, water is going to move out of one compartment to go into another. So this is just facts over here. We've dealt with a few of these different things here. Milliosmoles. An osmole is a number of, I don't want to get in too much into chemistry, but you've had chemistry before, so I'm not going to go into heavy. But it's the number of moles of solute, a number of solutes that contribute to the osmotic pressure of the solution. So how much of that is going to make that draw water towards itself? The osmotic oncotic pressure. And what it should be for inside and outside the cell is what we say is about 300 milliosmoles of liters, or per liter. That's what it should be inside the cell and outside the cell. If it's different, then water is going to move to that area, which I'll talk about. We also have something called milliequivalents. Milliequivalents, an equivalent is basically the number of moles of a given ion in a solution. We're going to talk about those terms in a little bit. But we have, let's say, 325 milliequivalents per liter. So how much of, say, sodium is in a liter is what they're talking about. How much of the solutes? Percent salt, the magic number that we're going to say is that we should have 0.9% sodium chloride inside the cell and outside the cell. When you get saline for your eyes, right, for do contact lenses, they will say that it's in 0.9% sodium chloride. It's not pure water. It's not a high dose of sodium chloride. It has to equal what your body is. Otherwise, water is going to change and it'll burn. So it has to be the same amount. Our magic number is going to be 0.9% sodium chloride. So, some important principles of fluids and electrolytes before we get into the nuts and bolts. Homeostatic mechanisms respond to changes in the extracellular fluid, not in the intracellular fluid. Intracellular fluid is not going to change much. It's hard to change inside the cell. But like in the plasma, we can easily change that by the foods that you're eating. Okay? You'll see that. There's no receptors that are directly, that will monitor directly the total fluid or electrolyte balance, but do this as an indirect mechanism through plasma volume and osmotic concentration. I'll show you what I mean. They kind of, the water will pass, but they don't need to go, the water molecules don't have to touch a receptor. It can go right through there, something called aquaporins. Okay? But it could pass right through there just because of the concentration. So cells cannot move water molecules by active transport. Water will go where there's going to be a higher amount of solute. So I always say water follows salt, or water follows solute. Where there's a higher concentration of solute, water is going to rush to that area to make a balance. So cells can't purposely get the water over there. They have to change the concentration. But inside the cell, it's hard to change the concentration. But outside the cell, it can. Okay? So those things you should know before we get into this. Now, what is osmosis? Osmosis is just simple diffusion. That's it. But it's simple diffusion of water molecules specifically. Going from a high concentration of water molecules to a low concentration of water molecules. But it's a number of particles per liter of the solution, not what these particles are. Okay? The particles have no reference to what it is. If there's 3 sodium over there and 2 potassium, and then there's 1 glucose and 4 chlorides, that's still 5 and 5 things on either side. It doesn't matter what those solutes are or what those chemicals are, but it's the number of particles on each side. So 2 proteins on one side does equal 2 sodium ions on the other because it's 2 and 2. So water won't move because of that, because there's an equal number on either side. But if there isn't, if there's, let's say, I'm just giving an example, there's 5 sodium over here and there's 2 potassium over here, water is going to go where there's more concentration, where there's more solutes. Okay? So water goes to the area where there's more salts and more solutes. Now, like I said, if you put sodium chloride in a container, this is the difference between an electrolyte and a non-electrolyte. And this explains a little bit why electrolytes have more of a drawing force, an osmotic force to them. When you put sodium chloride in a container, it breaks up into 2 parts. You put glucose into a container, it stays as glucose. So there's going to be more solutes in this area here, so it's going to be drawn, it's going to draw more water towards it. Does that make sense? Okay? So, if I give you something like this, where does it look like it's more concentrated? Inside the cell or outside the cell? Inside. Okay, there's more solutes in there. So which way is the water want to go? If this is a membrane of the cell, and the only thing that could pass through that membrane is water, water can leave the cell or can enter the cell. Those solutes, those green balls, or let's say sodium ions, they can't leave the cell or enter the cell. It's impermeable to the salt, but it is permeable to water. This is 2 containers, one here and one here. And one is more concentrated to the other. The only thing that could pass through that membrane is water. So which way does the water want to go? Into the cell or out of the cell? Into the cell. And when it goes into the cell, it's going to dilute that. So does that cell become bigger or smaller? Bigger, okay? So this is what we consider outside the cell is less concentrated than inside the cell. So we say that this cell is in a hypotonic solution. Hypo meaning it's less concentrated. Let's do the opposite. We're putting this cell, and again, that membrane, the only thing that can pass through it is water. Into the cell, out of the cell. You're putting this cell into a highly concentrated solution. There's more solutes out there. We're putting it in what we call a hypertonic solution. If we put a cell in a hypertonic solution, which way does the water want to go? Out of the cell or into the cell? Out of the cell. You see, it wants to try to dilute the outside, and this is a hypertonic solution. A good example of something like this is when you go to the beach and you go into the ocean. Now that ocean is very concentrated with salt, more concentrated than inside your own body. So you're putting your body into a hypertonic solution. Does that make sense? When you put your body in a hypertonic solution and you're in there in the salt water, water leaves your body. It'll try to do this. It won't, though. It's trying to dilute the ocean. So water is going to leave your body to try and dilute the ocean. If you're in there for 10 minutes, what happens to your fingers? What happens to the skin of your fingers? Yeah, they prune up, right? They shrivel up because water left your body. Now, what happens, as you've seen with fluids and electrolytes, urology and stuff, and circulation, is that when you lose a lot of water, you've got ADH that's going to kick in. You have aldosterone kicks in. You have the thirst mechanism that kicks in. That's why it doesn't happen. When you lose a lot of water in the ocean, you want to rush into the shore and get that fruit punch to get it back into your body. You get thirsty. So that's why it won't happen to us, because our body won't allow it, because we have all these mechanisms that go on. again, forget about these pictures here for the time being. If you take this over here where you're putting a cell that's concentrated into a hypotonic solution, the water goes into the cell or out of the cell? Into the cell. And that cell blows up. Gets bigger because water goes in. If you take this one over here, you take this cell and you put it into a hypertonic solution, water follows solute. Water follows where there's more concentrate of solute. So in this case, water will leave the cell or enter the cell? Leave the cell, and then you got a shriveled up cell over here. That's what happens when you go into the ocean. Your fingers don't prune up. And now the concentration is equal on both sides. Notice the spaces between them. When you put a cell into a what we call an isotonic solution, so it's the same amount of concentration inside the cell as outside the cell, the water doesn't go either or. It's perfect. Okay? So you should know what happens over here in terms of the cell. Does it expand? Does it shrivel? Hypertonic, hypotonic? This is what we're dealing with. So in a hypertonic solution, again, now we're using numbers. Look at the numbers here. The red blood cell, we say this is a red blood cell. A red blood cell, inside, as I told you before, is 0.9% sodium chloride. But the outside is 3% sodium chloride. For whatever reason, the food you're eating, whatever. Maybe put an IV in the person. So is 3% higher or lower than 0.9%? Higher. So in this case, you're putting this cell into a hypertonic solution. If that happens, which way does the fluid want to go? Into the cell or out of the cell? Out of the cell. And then what happens to your cell? No. It gets smaller, right? Fluid leaves it. All right? We say that the cell crenates. Crenation is this pruning or shriveling up. Okay? We could also take a red blood cell and put it into plasma that has 0.5% sodium chloride. So is 0.5% less concentrated or more concentrated? Less concentrated. So if that's so, inside the cell is more concentrated, which way does the water want to go? Into the cell or out of the cell? Into the cell. Okay? This is, and what happens to the cell itself? Yeah, it'll burst. It might get really big, but it can get to a point where it lyse and burst. Lyse means to burst, right? Like a balloon. Okay? This is why when nurses or whoever's going to put IVs in you, it's got to be the same amount of concentration inside the red blood cells. You see the bags over there, it's usually going to be 0.9% sodium chloride. What if you put water? Why can't you just put water into the bloodstream? What is that going to do to the cells? Is it more if you just put distilled water into the bloodstream, are you putting more concentrated fluid into your bloodstream or less? But the red blood cells are not changing. So you're putting the red blood cells in an environment that is hypotonic. What are the cells going to do in a hypotonic situation? Where it's going to be less concentrated. You put in this. So this is 0.5%, but I'm going to say 0.0% sodium chloride. In other words, you're putting distilled water. There is no sodium chloride. So that's going to be lower than this. So what happens to the cell? Or what happens to the water? Does it leave the cell or enter the cell? Enters the cell, and if you put distilled water in a person's blood, these cells, the red blood cells, will burst. That's why we can't put distilled water in them. It has to be 0.9%. Or something else that's called Ringer's lactate, which is all the other electrolytes in there. Some people, I like to use Ringer's lactate. But it's the same thing. We're going to give the same percentage that the red blood cells are. Does that make sense? That's the significance here. You need to understand that concept. And you can see where you could use this. Okay? And an isotonic solution, which is what you should be doing, if the red blood cell is 0.9% sodium chloride and you put an IV of fluid which is 0.9% sodium chloride, which way does the water want to go? Inside the cell or outside the cell? It's the same. Good. Neither way. Why couldn't immunology be like this, right? Because immunology is a story. This stuff makes sense. Okay? So we'll go a step further. If the bloodstream is 310 milliosmolarities, don't let those words, these units scare you. You just know that there's 310 concentration here, and inside the cell is 300. Which way is the water going to go? Is it going to go out of the, is it going to go from the bloodstream into the cells, or from the cells into the bloodstream?
From the...
Right, it goes from the cells into the bloodstream, so the cells will shrivel. Right? That's how you got to see it, and that's the significance. You've got to make sure you put in the same percentage. Now, we got to talk about these two words. They sound alike, and they have to do with the same thing, but it's not synonymous. Isomotic versus isotonic. Isomotic is the number of particles in the solution. So the particle concentration we're looking at. When two solutions have the same osmolarity. Now, the best way I could actually show you this is this, for you to understand this concept, is put a tube over here. Okay. So we have fluid in this pipeline. And we have a membrane over here that the only thing that's allowed to go across this membrane is water. And this is filled with water, this whole thing. Okay? Now, we can put certain things here. We can put, let's say the red here symbolizes sodium. The green will symbolize potassium. And the purple will symbolize chloride. Now, if you look at this, even though there are different particles in here on either side of where this membrane is, we have 5 of them total. 1, 2, 3, 4, 5. Over here, we have 1, 2, 3, 4, 5. There are different things in there, though. But because there's equal number of particles on either side, we say that it is isomotic. Does that make sense? Then we have isotonic. Isotonic is there going to be fluid movement going on here? Even though there's 5 particles here and 5 particles here, it is isomotic, but it's not isotonic. Isn't this side more concentrated than this side over here? Isn't there more water over here than it is over here? So it's not isotonic. It's hypertonic here, and it's hypotonic here. So this is isomotic because there's the same number of particles on either side, but it's not isotonic. It becomes isotonic until after the movement happens. This will go up, this will go down, so that it moves like that. So that now there's going to be equal concentration on either side. Does that make sense? Now it's isomotic. We want to make sure that the fluids that go into your bloodstream are isotonic and isomotic. The isomotic will make sure that the isotonicity occurs, that it stays the same. This is saying that 0.9% of sodium chloride fluids that's coming in is saying that the same number of particles that you're putting into the blood through the IV is the same number of particles that would be located inside the red blood cell. So in that case, the saline that you're putting into the bloodstream is isomotic. And because there is no fluid movement going on into the red blood cell or out of the red blood cell, it's also isotonic. But they are not the same thing. Is that clear about that? Okay?
That's what they do for tonic water.
What's that?
The tonic water.
Yeah, tonic water has nothing to do with this. That's the carbon dioxide stuff. Yeah, that's totally different. They just call that because the carbon dioxide gives the bubbles in tonic. I don't know. All right, does that make sense though? So let's put this together in a real case situation. Michael has recently started working outdoors in the hot weather to earn money for his tuition. After a few days, he experiences headaches, low blood pressure, and a rapid heart rate. His blood sodium was down to 125 milliequivalents. The normal is about 144 milliequivalents per liter. How do you explain this? Why did the concentration of his plasma sodium go down? Where did the salts go? He sweated it out. Okay? So Michael lost the sodium through perspiration. You all perspire. If you sweat on above your lip and you taste it salty, there's a lot of salts in there. So the low sodium in his blood allowed fluid to move into the cells by osmosis. Think about that. There's less sodium that's in the bloodstream because you just sweated it out. So that means that there's less concentration in the blood compared to the red blood cells and all your other cells. Does that make sense? And when that happens, the low sodium in his blood is allowed to move the fluid into the cells by osmosis. Because therefore, if you're basically the cells are in a hypotonic solution because you just sweated off a lot of those salts. So now fluid is going to go from the bloodstream into the cells. Does that make sense? And if it goes into the cells of your brain, it can cause headaches. It swells up. Okay? So lack of fluid lowered his blood pressure to give him a headache. All right? There's not much blood pressure getting up there, but they'll also swell. And the increased heart rate occurs because there's less blood flow, right? We learned about that. And it tries to keep the blood pressure up, so your heart rate goes faster, trying to push it up. Right? When you go up a hill, you're going very slow when you're driving. What's the first instinct you have? Floor on the gas pedal. To try and get you more pump up there so you can get up there faster. Okay? Let's look at this case. Frank has hypertension. His doctor has advised Frank to stay on a low-salt diet. Frank consumed a lot of salt the day before his last checkup, and his blood pressure was up. Why? When you eat foods, right into the bloodstream. So now you have an extra amount of salt, sodium and stuff into the bloodstream. So compared to the red blood cells and all your cells in your body, your cells are now in a hypertonic solution. So think about it. What's going to happen? Where's the fluid going or coming from? What's going on here? Your plasma is more concentrated with sodium. So what's going to happen? You got to think of this stuff. Right, but where's the water going? And where's it coming from? You got it right. Cells which shrivel, but what's because of why? Because water is leaving the cells to go to a. It's like you're putting your body into a salt water. If you're the cell, water is going to leave and go into the bloodstream. Does it make sense? That means you're putting more blood volume, water volume, into the bloodstream. If you increase blood volume, what does that do to blood pressure? It increases, right? So that's what happened. The extra salt that Frank ate made his blood more hypertonic. So the hypertonic blood will attract fluids from the body cells by osmosis. And you're going to have a blood volume that's going to increase, which means your blood pressure is going to increase. That's why people who have high blood pressure, they're on a low-salt diet. You've heard of that. Now you understand why. It's like a big sponge. If there's more salt, there's going to be more water that's going to be attracted to it. Is that clear?